Okay, at this point in the seminar, we have covered the basics, and now it's time to look at some of the more interesting stuff. In fact, the next main result that we're going to cover is Gödel's first incompleteness theorem. So we're going to be concerning ourselves with the proof of this, and I think this will take me the next few lectures in order to do so. Okay, so Gödel's first incompleteness theorem holds in a very broad setting. Indeed, we have the following vague way of expressing Gödel's first incompleteness theorem, which I'll write down. So here's the vague statement. Let T be a formal system. Expressing arithmetic. And we make the assumption that the axioms of this system, as well as the deduction rules, are both sets which are computable. Then T is necessarily either incomplete or inconsistent. Okay, now, in fact, these are the kinds of statements that have kind of always made me angry when I've come across Gödel's incompleteness theorem, although after tackling it inside my mind, I did decide to present one to begin with. So the point is that we're going to come across a philosophy and a method inside the proof of a rigorous statement, which I will give at some point. And that proof method and the proof technique is going to be generalizable to a huge array of situations. Now, I'm going to try to make that generalization as rigorous as possible, but this is one of the common points of confusion for Gödel's first incompleteness theorem. It seems a little bit hard to swallow because we have these vague ways of describing the generality within which Gödel's first incompleteness theorem holds. Okay, I suppose I'm talking as though Gödel's first incompleteness theorem is already, has been heard about from the audience or is known to some degree. So to those who haven't come across it before, it's an extremely important fundamental theorem about the nature of mathematics and formal systems. And expressed extremely vaguely, it says here that you're a little bit doomed if you're going to come up with some kind of computable system of mathematics. There's no chance of you achieving consistency and completeness because surely within your mathematics you want to be able to describe arithmetic, and once you can, the system admits paradoxical statements which will render the entire logic either inconsistent or incomplete.
Maybe you could characterize what you mean in a simple way by arithmetic. Like, what are you asking for there?
Yeah, so all I'm asking for there is the basic properties of the natural numbers as well as addition and multiplication. So I want basic laws such as multiplication by 0 is equal to 0 and addition by 0 leaves the number invariant, etc. So just the very, very basic fundamentals of arithmetic, although we do need to make sure that we at least have addition and multiplication, because there is a result that if you're only looking at a first order theory that expresses the basics of addition and no multiplication, then that system is computable. I believe that's correct. Could I just get Billy to confirm that, please?
Yeah, that's known as Presburger arithmetic, I think.
Okay, cool. All right, great. So the goal of today's lecture is to slowly make this vague statement more precise, and then we can get started with the very beginnings of this proof. One last thing that I would say, just by way of introduction, is over the course of learning this argument, I have completely fallen in love with this result as well as the argument used for it. So I'm very excited to be presenting it, and hopefully the audience enjoys it in the same way that I do by the end. Okay, so there's a lot to make precise here. So let me underline it, formal system of arithmetic. His set of axioms and deductionals are both computable. So this will take us a little bit of time. To get started, let me draw out the exact first order language that we are going to be using. Okay, so this is a proper definition now. We define the first order theory, which I'm going to be labeling Q, and it consists of the following aspects of the language, followed by the axioms which will define the theory. So we have a single source, which I'll label A. We have 4 function symbols. These are 0, the successor, plus, and multiplication. Let me get rid of this. Okay, I can see a big black line through my entire board. I don't know if other people can see that. Nice, it disappeared. Okay, so these are our 4 function symbols, and then I'll crush in the right here that we have no relation symbols. Okay, so that's the language, and now I wish to define the theory, and we have 7 axioms, so I'm out of space. Let's move over to the next board. So this is still part of the same definition. Okay, and this is making formal what I mean by the basics of arithmetic. So you'll see that all of these are very basic axioms. We ask that no number is equal to its own successor.
I don't remember, did you mention what successor is?
No, I didn't mention that. So far I've defined it as just a one-ary function symbol, but the actual function from the natural numbers to the natural numbers, which is known as the successor function, is just the function x maps to x plus 1. So it just adds 1 to the argument. Second axiom states that this function is injective. Third axiom states that all non-zero natural numbers are the successor of some number. Fourth axiom states that addition on the right by 0 leaves the number invariant. We have this next rule about how the successor interacts with addition. Multiplication on the right by 0 is equal to 0. And then lastly, we have the way that successor interacts with multiplication. Good. And that's the end of my definition. So this is the first order theory that we will be considering. We're going to be labeling it Q. In literature, it's often referred to as Robinson arithmetic, and one may or may not recognize this as the familiar axioms of piano arithmetic, but with the induction axiom omitted. The point is that the induction axiom is a bit difficult to write down if you insist for it to be a first order theory, and it's not in fact used at any point inside Gödel's first, the proof of Gödel's first incompleteness theorem. And so it's simpler to work with Q, and so that's what we work with. Okay, now I need to make a point. It is not that surprising that this system Q is incomplete, right? Because if you think about it, we have omitted the inductive axiom. So it's not far-fetched to believe that there are some statements about the natural numbers which require crucially the power of induction, which are therefore not going to be provable within the system. Indeed, this is true. So Q is incomplete rather trivially. It can be proved, and I've linked to proof in the notes. I won't go through it now, though, that the following statements cannot be proved or disproved inside Robinson arithmetic. So don't get this confused with axiom number 4, which states that addition on the right by 0 leaves a number invariance. This is addition by 0 on the left. And this formula cannot be proved, and it cannot be disproved inside Q. So I can write that out. Q does not prove 4x 0 plus x equals 0, and Q does not prove the negation of the same result. Okay, so the fact that Q, if it's consistent, is an incomplete first order theory is not the interesting part. What we're more interested in is the fact that that Q is incomplete and it cannot be completed. There is no extension to the logic Q that will render the system complete. So in some sense, Q is uncompletable. Okay, let me move to the next board in order to write something
just before you
about
do that.
Yeah.
Sorry, one second. I should probably address with your definition of complete here. Well, firstly, could you clarify, is Q just this set of 7 axioms, or is Q the set of all provable consequences of those axioms?
So I just mean for Q to be this set of axioms, but then we also include all of the derivable formulas via natural deduction, which you introduced.
Right, because to preserve the same definition we've been using for complete, it would, if it was just the set of axioms, it would be even more trivial, because like the statement 1 equals 1 is not amongst those axioms, so therefore it's incomplete based on the definition I gave earlier in the seminar, that a set of formulas is complete if and only if for any formula either it or its negation is in the set of formulas.
Right, I see.
Yeah,
so that's not what I mean.
The definition of complete and whether or not a theory is just the axioms or the consequences of some axioms, those two things kind of go hand in hand. Sorry, I meant to talk to you about this before we began.
That's okay. We can point that out. So Q being, let's not write Q. A first order theory L is incomplete if how to say this, if there exists a formula phi such that L hat does not prove phi, and L hat does not prove the negation of phi, where L hat is the set of all provable formulas.
Okay.
Yeah, using okay, that's okay, right?
Mm-hmm.
Okay, good. So I've defined incomplete there. So that's the notion of incomplete that I'm using for these lectures. Differs slightly from what Billy wrote. That's fine. All right, let's move to the next board. Okay, so with that definition that we just gave, it's important to realize that Billy has already proven inside this lecture series that Q is completable. In fact, all first order, or all consistent first order theories are. So let me just remind people of that. So Billy showed us
You make me sound like a cult leader or something.
I'm not convinced you're not. Inconsistent first order theory L is completable. So more precisely, there exists a first order theory L star for which every single axiom inside L is provable inside L star, and L star is consistent and complete, right? So there exists a first order theory Q star satisfying that every axiom in Q is provable in Q star, and also Q star is consistent and complete. No, this is assuming, which we haven't shown, that Q is consistent. Okay, so this is a subtle point, and this is really important. A lot of people misunderstand Gödel's incompleteness theorem to say that if you have a consistent first order theory, which is strong enough in order to describe the basic laws of arithmetic, then that system is necessarily incomplete. This is not what Gödel's first incompleteness theorem says, and indeed it's not even true, right? So we have just shown that this first order theory Q exists, and it's capable of expressing arithmetic in enough of a way that what we end up proving Gödel's first incompleteness theorem to be true is sufficient for, and yet there is a parent system, Q asterisk, which is consistent and complete and contains Q, right? So going back to our vague statement of Gödel's incompleteness theorem that I wrote right at the very start, I had this phrase, whose set of axioms and set of deduction rules are both computable, right? This cannot be ignored. It's very important. So indeed, this is the next part, which I need to make precise. And this is made precise in Gödel's original paper, as well as in what we'll be doing throughout this lecture series, via a notion of primitive recursive functions.
What I've often found in other sources is that so a lot of people often say a formal system at the start of their like statement of incompleteness, and hidden in that is like they just haven't stated that what they mean by a formal, like they would say that a thing with like non-computable axioms wouldn't count as a formal system.
Wouldn't count. Right, I see. Oh, that makes sense. That's probably why this misconception exists. I think this is an extremely important part of Gödel's theorem. In fact, I basically think that it's the content of it. Okay, so I'm not going to define primitive recursive functions and relations today. I guess I might, but I probably won't. We will at some point. But let me write the phrase on the board, and then let me say something brief about it. Okay, so as I said, I'm not going to formally define it right here, right now, but just so that you at least have something inside your head, they are certain types of functions from some product of the natural numbers to some other product of the natural numbers. So if you consider the full set of all such functions, we're going to carve out a subset of them, and that subset is going to be the primitive recursive functions. Okay, since Gödel's introduction of these functions inside his original paper, the primitive recursive functions have found themselves to be an important object inside general theory of computation. This fact about the primitive recursive functions is not relevant to Gödel's theorem. It's helpful and it's part of the philosophy, post haste, but we're not going to use the fact that the primitive recursive functions have anything to do with computability throughout the entire argument. So instead, the role that they are going to play is they're going to carve out a certain set of relations that satisfy a criteria, and then that criteria is going to be crucially used for the construction of the so-called Gödel sentence, which is the core object inside the proof of the theorem. So for now, the way that we're thinking about primitive recursive functions is that they are a class of functions which satisfy so there's a proposition about them which describes a property of theirs, and that property is going to be an important part. I will write out that property. That's what I'm going to do next. Okay, so let me move to the first board again.
You sort of pointed out that for the purpose of your proof, it doesn't matter that they correspond to computation in any sense, but it's still important that in the statement of the proof and the sort of weight of the proof is a sort of understanding that wanting the set of axioms to be primitive recursive is like a reasonable expectation, because if it's just some like arbitrary class of like functions, then who cares? But yeah, that sort of expectation of like knowing that I guess they correspond in some way to computability is still an important part of the theorem, if not the proof.
Yeah, I see. Yeah, that's a good point. So to justify that these are a reasonable expectation, you do want to use the fact that they correspond to the computable functions, because you want your system of logic to be computable, because you want to be able to use it and you want to be able to engage with it. So yeah, that's a good point. This is a reasonable expectation in order to ask for this. Okay. The property that I've promised you that the primitive recursive relations satisfy, it's most easily expressed once you have this notion of Gödel numbering, which is another main object inside the proof of Gödel's first incompleteness theorem. So this is rather simple anyway. So let me just quickly say a sentence about that, and then I'll give the proposition which I promised. Okay, so again, this is going to be a little bit vague. So Gödel numbering is a way of associating a natural number to each formula inside Q. So Gödel numbering is a particular way of doing this. We will introduce a specific Gödel numbering later in this lecture, hopefully, if I've got time for it. But for now, just think about it as we have some way of injecting the formulas into the natural numbers. This is not so surprising that we can do it in the modern day. I don't think it was very surprising that this was achievable back when Gödel first wrote this proof either. But for now, just to convince you that this is reasonable and indeed simple, just think about the binary representation of natural language that computers use. So if I have a chunk of text on a page, we can associate to each of those characters a binary sequence and then concatenate the entirety of all of those binary sequences, and we get some huge mega number. And then we can just read that as an integer. It's an integer that only consists of ones and zeros, but who cares? That's some number out there, right? And so that's literally what we're going to do with Gödel numbering. We're going to just come up with a way of associating to each formula inside Q a natural number. There are many different ways that you can do this, and the technicalities of the way that it's done is not important to Gödel's theorem. However, we do need it to satisfy some criterion, the most important of which is that it's injective. So if we have a number, a natural number, and we're told that this is associated to some formula, we need to be able to extract that formula. So it's important that this mapping from phi to the caret brackets phi is injective. Okay. And I'll introduce a little bit of notation as well. So I'm about to write down the proposition, but in the following I will write n underline for the term in Q associated to the natural number n. Right, so for example, 2 underline, oh, I won't write equals, that's confusing. Okay, so to underline is simply notation for the successor of the successor of 0. Okay, now with all of that said, let me give you the proposition, which is the important property that the primitive recursive functions / relations satisfy. And recall, I haven't told you what the primitive recursive relations are yet, but I'm about to tell you something that they satisfy. Oh, wait, I've written this wrong in the notes. So let me fix that.
Sorry, what was that?
Sorry, I just muttered under my breath and I had written something incorrectly in the notes.
Oh, okay.
So, but I've written it correctly on the board now.
Can I just fuss a little about notation?
Sure.
Just to be clear, so there's 3 different levels of things here. There's the first order language in which S of 0, that's where that lives. It's one of the terms of that language. And then there's the set of natural numbers where something like 2 lives. Then when we write things like 2 underline, this is sort of meta syntax, which is just it's on the level that we are speaking, we are sort of making a reference to the term S of 0, and it's not like a component of the language that's underlining. And in a similar way, the quotes, putting quotes around a formula isn't the quotes aren't a piece of the actual first order language's syntax. We're making a reference to a number, which corresponds to it under this Gödel numbering. And so I guess, as you've written here, you've got a number with quotes around it and then underlining it. So there's sort of 3 different steps there. That's probably confusing if you're not paying attention.
Yeah, absolutely. So this is a bit confusing if you're not paying attention. And indeed, this is the core of the argument. So I think that proposition, this proposition, which I've just written down, is the key. I guess I'd say there's 2 of them. There's 2 key realizations that make Gödel's first incompleteness theorem transparent, and this is absolutely one of them. So let's go through this and make sure that it makes sense. I'm just going to read this bottom line very carefully. So what I've said here is if M1 through to Mn is an element of R, right? So let's think about it. R is a relation, right? So R is some subset of this n-fold product of the natural numbers, right? And then M1 through to Mn is an element of that. So here, M1 through to Mn, that's a sequence of familiar, comfortable, natural numbers, right? They're not appearing in any formal first order theory. They are just M1 through to Mn might be 5, 1, up to 9 or whatever. And we're literally thinking about those natural numbers there. Okay, and what this proposition says is that if R is primitive recursive, then there exists a formula R underline in Q. So this is a formula inside the first order theory Q, which satisfies the property that Q is able to prove R underline applied to the following terms. And what are these terms? Well, let me spell it out for you. If I had M1 underline, then the point is M1 is an actual number, and then M1 underline is that term, is that term inside Q that represents M1. So this is I should write equals. I think that's more confusing. So M1 is the successor of the successor of the successor of something. Cool. And then when I take the angle brackets of this, or what Billy was referring to as the quotations, what that means is we now read M1 underline as some term inside our language, and we have the Gödel numbering, which associates to each such thing an integer.
You should have probably said
wait. No, I should
every
have said that
formula
wrong.
and term.
Yeah. Sorry. Damn, how annoying. Okay, let's do that again. So M1 underline is the term inside Q, which is the successor of the successor of blah, 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 of the successor of 0. And then when I put angle brackets around that, oh, hold on. I've written the statement wrong. I shouldn't even have these.
Right, okay. I thought that was...
Yeah.
That makes more sense.
With the quotation marks, with the quotation marks, that's an actual integer. Okay, that's why I fumbled over my words. Okay, and that's in literally the most important part. So in fact, maybe we can edit this. Let me go back.
It's still true that the Gödel numbering is important for the terms, right?
I don't think it even is, right? Because I'm just going to R underline is a relation symbol, and it's ready to receive terms. And the terms that I give it are M1 underline up to MN underline. And
yeah, I just mean elsewhere in the proof. But I mean, in a way, if you encode all the formulas, then you kind of indirectly encode all of the terms anyway in some way that could be recovered and recognized. Like you've got all the terms x equals 0 for every single term. Like you've got all the formulas x equals 0 for every formula, also for every term x.
Yeah. Yeah, but I don't need that for this proposition, which I said that I do.
Right, I didn't intend to.
Yeah, let me check in my head 1 second. So if M1 up to Mn are in this relation, then Q proves R underline of, yeah, I just shouldn't have those quotations. Okay.
Do you want this to be a proper cut in the edit of this recording?
Maybe. I just think it's frustrating that this is such a it's the core of the argument, and I just wrote it down wrong and then said it wrong. I guess I don't really mind. Either or, but let me get the correct statement down. Okay, let R be a subset of the natural numbers taken to some n-fold product. If this relation is primitive recursive, then it satisfies the following condition. There exists some formula R underline in Q. Oh, I've written this wrong as well. Okay. So it's not that there exists integers, it's that all sets of integers satisfy the following. God. Okay. There exists a formula R underline in Q satisfying if x1 up to xn is some vector, then we have I guess I should write it. x1, what happened there? x1 up to xn is an element of R, implies that Q, let's make that look like irrational numbers, Q can prove underline of x1 underline up to xn underline. Okay, cool. That's the correct statement. So let's go through this very carefully and make sure that the statement makes sense, because this is the most important proposition. At least, sorry, as I said, there are two important propositions, and this is one of them. So what we have here, x1 through to xn, this is just a sequence of natural numbers, right? So they're not terms inside the first order theory Q, they're just natural numbers, x1 up to xn. And then if they are inside this relation R, then it can be proved inside Q. So Q proves that this relation holds, which is R underline applied to the terms x1 underline up to xn underline. Okay, I think that's clear enough. Did you want to make any comments, Billy?
Is this supposed to be weak representability?
Oh yeah, this is right. I guess I haven't written either. So
I remember the something like this that had like a, if x1 up to x1 xn is not in R, then it also implies something.
Yeah. So that is true of the primitive recursive functions. So let's put that in as well.
Oh, okay. Yeah. So this is that definition.
Yeah. So this is representable. So this theorem says the primitive recursive functions are strongly representable.
Okay. Yep.
Cool. Makes sense.
Yeah. Yeah, and I'm really realizing even if you took away this second line, it wouldn't be weak representability.
No, it wouldn't. Yeah.
Because you need the, like, without this second line, this is unsurprising because you can just take you can make R underline just be a tautology formula. Because then it's always true that Q proves it.
Yeah.
But yeah, okay.
Yeah, agreed. So this is the important part. Yeah, the second part is what makes it non-trivial, as you just said. Okay, that's good. So now with the notion of primitive recursive relation on paper, and what I mean by that is the property that they satisfy on paper, I can now define what it means for a first-order theory to be effectively completable, which is going to be our formal notion of these computability statements that I've been making. Okay, so I'll move to the next board. Okay, so here's another proper definition. I'm defining what it means for a first-order theory to be effectively completable.
Saying completable, right? Not computable.
Completable, yeah. That's what I wrote, right? Okay. Okay, so I've written that the characteristic function of the set of axioms of L prime is primitive recursive. So let me say out loud what I mean by that. We take the set of all of the axioms of L prime. Now, all of these are formulas inside the first order theory L prime. And so associated to each one of those is a integer corresponding to the Gödel numbering of that formula. And so we now have a function, which I'm calling the characteristic function, from a subset of a product of the natural numbers to the natural numbers, which maps a natural number to 1 if it is the Gödel number of one of the axioms inside L prime. And it maps all other natural numbers to 0. So that's what I mean by the characteristic function. It identifies whether there is a axiom inside L prime associated to the natural number in question. Okay, and we ask this of the deduction rules as well, the set of deduction rules.
Another way to make it line up with the definition of primitive recursive properly is to replace set of with set of Gödel encodings of.
Yeah. Yeah, that makes sense. Okay, so that's I've written down the 2 dot points corresponding to the computability aspect of it. And now we just want to write down that L prime is an extension of L. So every axiom rule, or every axiom, let's just say, every axiom of L is provable in L prime. And then lastly, L prime is complete. Okay, so we're very close to being able to state our precise statement of Gödel's first incompleteness theorem. But just before I do that, I thought that I would make a historical remark, because this is something that confused me a little bit. So if you decide to go back and read Gödel's original paper, then you'll see that there's this concept of omega consistency kind of written all throughout the paper. So when I was first reading this, I found this omega consistency statement everywhere, and I got frustrated. I was like, where's the real result? Where's the real result where it's just consistency? Because, that's the famous thing that I've heard of. And the truth is that Gödel never proved his statement for consistency. He only ever proved it with this notion of omega consistency, which is a strictly stronger property of a first order theory than of that of consistency. Indeed, it was Barclay-Rosser who, in a later paper, extended Gödel's results out to the familiar one that we all have heard of before, which is the statement about consistency versus completability. Okay, so at this exact point in time, I haven't quite decided whether I'll present Ross's generalization out to consistency. But one remark that I will make about it is that it doesn't hold inside it the deep part of Gödel's theorem. So we still have the philosophical significance of Gödel's first incompleteness theorem, even if we concern ourselves with omega consistency the entire way through. Okay, so let me just make a little point about this. I'm not going to bother with defining omega consistency today. I will properly later, but I'll mention that it's a strictly stronger property that could or could not hold of a first order theory than that of consistency.
just want to add, I think it's probably debatable, like the significance or like importance of that generalization to like the weight of the theorem. I'm still sort of unsure of that.
Sure. My current understanding is that Rosser did a bit of like a technical argument in order to just get that extension. And I don't think it was like, I don't think in his paper you have some fundamental definition like primitive recursive inside Gödel's original one, for instance.
I can imagine like maybe the proof of the generalization is like a lot of uninteresting technical details, but I think the like content of the statement and like the fact that it still holds if you're just consistent. I think there's a sort of significant difference between omega consistency and consistency, especially in the context of completeness.
Sure. Okay, Rosser extended Gödel's result to ordinary consistency. That's what I've written in the corner there. All right, so now we can put down the precise version of the vague statement that I started with, but I'll need another board for that. Cool, and that's it. If Q is omega consistent, then Q is not effectively completable. All right. I'll write a very brief summary.
Wait, before you do that,
yeah, you want to say something?
What's the then? Did you mean to mention consistency in the effectively completable statement? Yeah, because if you don't require L prime to be consistent. Sorry, could you still hear me when I was talking there?
Oh, I see what you're saying. So you're saying there's the threat that the original L is not omega consistent. Is that what you're talking about?
Well, more importantly, you could like this. I think, as stated, it's false because if you take L prime as just make the inconsistent theory, then I believe everything is true there. So I think to fix it, I would just say include omega consistency as a premise to it, and as a property of L prime.
Oh, I see. So you want the original system to be omega consistent, and you want to preserve that as you extend it. Is that what you're saying?
Yeah.
Yeah, okay, that makes sense. Yeah, that is necessary. That's a good point. So how do I do this for the sake of the recording? Do I need to do anything? Do I need to move back over to the board, or can I just click on it and make a change?
Like the camera.
Yeah. Oh, okay. Okay, so I've added omega consistency to one of the hypotheses on the first order theory L. And I'm going to add a dot point on the conditions of L prime, which is the same thing. Because we want omega consistency to be preserved throughout the extension as well. And we want it to be there in the first place. Okay, does that resolve your issue, Billy?
Yeah.
Okay, good. Thanks for that. That's important. All right, let's go back to the other board. Okay, I'm running out of time, so let me just quickly do this summary and then I'll wrap up. So there are three important notions or definitions. And they are Gödel numbering, primitive recursive functions and relations, and then the last one, which I haven't even mentioned yet, is the Gödel sentence, which depends on the first order theory that you have, G sub Q. And this is going to be used in order to finish off the argument once we've set all of these pieces up. And all I'll say about it is that it is a formula inside Q that satisfies the following. If Q is consistent, and this is ordinary consistency, then it cannot prove Gödel statement. And if Q is omega consistent, then Q cannot prove the negation of the Gödel sentence. And hence, if Q is omega consistent, Q is incomplete. Okay, I'll leave it for there for today. Any questions or comments?
That was great. Good overview.
Thanks. Yeah, nice. Hopefully there was something helpful there. No questions? All right, next time I'm going to talk about Gödel numbering, and I'll probably have time to at least give the definition of primitive recursive functions. And then the lecture after that is going to be tackling the very important proof, which is that the primitive recursive functions are strongly representable. So tune in for that. Thank you.
So we have like half an hour break now, right?